Hello, everyone, and welcome to another SETI Live. I believe, let me just check my notes here, that this is our third SETI Live of the day and our fourth one of the week. So whether it is your first one today or your first one this week or your first one ever, we are thrilled to have you here. So thank you so much for joining us. If we were going to search for signs of life on an exoplanet, what should we look for? When it comes to planets that are hosting life, our current sample is one, Earth. So how could we design a small satellite mission to take whole Earth spectra in order to measure the temporal variability of spectra from an inhabited planet with an illumination phase, rotation, cloud cover, and seasons? The data would help models of habitable planets, guide analysis of exoplanet atmospheric measurements, and inform instrumentation for future NASA missions to search for signs of life on exoplanets. Joining me today is SETI Institute astronomer Doug Caldwell and his undergraduate student Jorge Coppin, and they're here to tell us just how they're going to tackle this challenge. Thank you, Doug. Thank you, Jorge, for joining us today.
Sure. Thanks for having us.
Yeah, thank you.
So Doug, can you tell us a little bit about what the research project is that you have given to Jorge this summer?
So as you mentioned, one of the big goals of NASA that NASA is undertaking now is to look for life elsewhere in the universe. And one of the ways we're doing that is looking at extrasolar planets or planets around other stars. And from those planets, which are very distant, we can only get some very basic measurements. And if we use a really big telescope, we can measure their atmosphere to see that they even have an atmosphere. That's the first question. And then if they do have an atmosphere, what's it made of? And we can start to see if there's hydrogen, carbon dioxide, water even in these atmospheres. And so our next question is, well, is there anything in the atmosphere that might tell us that there's life on that planet? Like for instance, on the Earth, we have oxygen and we have methane and we have these gases that are generated by life on the Earth. And so we're hoping we can use those, seeing those on other planets to decide if that means there's life. But that's complicated because there could be other reasons why those gases might be on those planets. They might come out of volcanoes or whatever chemical process is going on in the atmospheres of these planets. And so one of the real questions that we have is, if we see something, what does that mean? What does that tell us about that planet? And the one case that we know there's life, as you mentioned, is the Earth. And so what our project is hoping to do is to take observations of the Earth to sort of understand the range of things we can see from a planet that we know has life, and hopefully help let that guide us interpreting the measurements we can get in the future from these other planets that we're trying to decide if that indicates life or not. So our project goal is basically to develop a small telescope that we can put in space to stare back at the Earth and take measurements as if it were an exoplanet. So we're not trying to resolve the cities and the houses and read people's license plates. We're really trying to just see the entire Earth and what the signal from that looks like, the spectral signal, the infrared signal, the visible signal. Is there polarization in the atmosphere that might indicate water and other things in the atmosphere that could indicate life? And this sounds like, surely this has been done before, right? We're looking at the Earth. Well, we have been looking at the Earth a lot, and Jorge has some great examples, and I'll let him go into it. But the goal of our project is to look at the Earth as an exoplanet, not look in detail at the detailed weather that's coming, tomorrow to California, but really, what does the whole Earth look like? And we surprisingly haven't done that very much. And so that's what we're hoping to do with this little satellite.
Okay. Well, I understand Jorge has a small presentation, but first I'm gonna give some shout outs. So let us know where you are watching from. Right now we have viewers from Switzerland, New Hampshire, the UK, and Florida, Los Angeles. So thank you all for watching. Please continue to let us know where you're watching from. And as a reminder, we are a nonprofit and we do present these as our educational outreach. So if you want to continue supporting us, your bits, your subs, your stars, your super chats, all of those go to this program and to help us continue doing this kind of outreach. So we appreciate everything that you guys do. All right, Jorge, are you ready to give us your few slides here?
Yeah. I'm going to present my slides. We've been looking at the Earth, like my mentor mentioned, for a very long time. Since we started sending spacecraft just to be able to look at the Earth, but specifically, uh, just looking at the Earth from a distance. This is the first image of the Earth taken from the distance of the Moon. It was taken in August 23, 1966 by the Lunar Orbiter 1. As you can see, it's not a very pretty image. The data that we got from those early satellites was really rough. But then, just 2 years later, we had the aptly titled Earthrise photograph. It was taken from lunar orbit by Apollo 8 astronaut William Anders on December 24th, 1968. And this gave us really the first colored images of the whole Earth, in really high definition, which gave us a new perspective about us as humans, just living on our planet. Forwarding a little bit, in December 7, 1972, Apollo astronauts Harrison Schmitt and Ron Edwards took this picture of the Earth from about 29,000 kilometers. Uh, and it was named the Blue Marble, just because they were able to get the entire Earth during the daylight. And to this day, this remains one of the most reproduced images in history, meaning that, to us as humans and as a species, just being able to look at ourselves from far away is something that's important and impactful. Uh, so, what we see here is a picture some of you may recognize. This is the pale blue dot photograph taken by the uh, Voyager 1 spacecraft as it was, leaving the solar system in February 14, 1990. This picture came from a campaign at the request of the astronomer Carl Sagan, who was the one who also coined the term pale blue dot in reflection of the image significance to him. And in many ways, Carl Sagan was ahead of his time. In this picture, the apparent size of the Earth is about less than half the size of a pixel. Of course, here it's a little bit bigger because I zoomed in, otherwise, it would have been hard to look at. Uh, but this size of what we could see of the Earth taken from such a far distance, about 6 billion kilometers from the distance of the Earth, is magnitudes of size bigger than any direct image of an Earth-sized exoplanet that we could take with future explorers in the future. So it just sort of gives us a feel of what it would be to look like at Earth as it was an exoplanet. And it was one of the first times we started thinking about that. So Sagan himself in 1993 published an article in Nature detailing the use of the Galileo spacecraft when it had an Earth flyby to look for signs of life, or what we otherwise know as biosignatures. Now, we know that planet Earth has life, so why do we try to prove that Earth has lives? Well, Earth, as my mentor mentioned, is the only known, habitable and inhabited world for life as we know it. So when we look for exoplanet candidates which could harbor life, we must know what we're going to, what we want to find, and we want to probably find something similar to what we see here on Earth, and it's something that we call a ground truth. And Sagan's article kicked off the study of, just Earth habitability as a whole, and laid out the original groundwork, many years ago, for what this kind of science is. Uh, mm, More recent missions like Epoxy have done sort of similar science of looking at the Earth from far away and studying as if it was an exoplanetary world. Uh, and there's also been other more creative methods of just looking at the Earth by using the reflection of Earthshine on the Moon's surface to sort of study the Earth as it was transiting exoplanet. Uh, but these methods have been few and far in between, and a lot of them have been proven to be extremely difficult. Like just looking at the Earth shine on the moon's surface. So this is why me and my mentor are proposing a dedicated small spacecraft mission for studying the unresolved Earth as an exoplanet. Now, we have many weather monitoring satellites, and people may ask, why don't we just use those? Well, Earth monitoring satellites use a variety of orbits and have a variety of instruments for the purpose that they were created for. And a lot of these satellites mainly orbit around low Earth orbit, or what we call geostationary orbit. And these orbits really don't work for a dedicated mission to study the Earth as an exoplanet, since low Earth orbit is too close to the Earth's surface to just look at the whole Earth disk in one view, while geostationary orbits stay over the same region of the surface at all times. Which doesn't really give you a lot of variability when it comes to just looking at the different seasons, or how the spectral data would change if you're looking at land versus looking at ocean, things like that. There's also spacecraft, weather satellite spacecrafts like the Discover satellite, which took the set of images you're looking at right now, one of the moon transiting in front of the Earth, and one of the moon's shadow during a lunar eclipse. And you may ask, well, why isn't the spacecraft perfect for looking at the Earth as an exoplanet? Well, the spacecraft is what we call Earth-Sun Lagrange point, and it's in the L2 Lagrange point, which means that you only get to look at it in the daylight side, meaning that we don't really get that variability that comes from looking at the Earth during the day or the night cycle. So currently, the way we study potentially habitable exoplanets is by looking at their spectral footprints. And this allows us to know what their atmospheres are made out of. And it helps us find different biosignatures. So to study the Earth in a similar manner, we want to collect spectral data of the variable Earth to take into account, the important things like the illumination phase, rotation, the cloud cover, and the seasons, so that we can inform future exoplanetary missions. Most soon, probably the James Webb Space Telescope and other future proposed missions like HABEX or LUVOIR. And this is the end of my presentation. To just give a little bit of overview about why we're doing this, and next we're going to probably talk about how we're going to do it.
All right, thank you, Jorge. I'm going to do a quick shout out to a bunch more people watching from Australia, Connecticut, Puerto Rico, Canada, New York City, Utah, Olympia, Washington, Mexico City, Portugal, and Germany. Wow, we have a pretty global audience going this evening. Thank you, everybody, again, for joining us. So Jorge, you gave us the overview of the why, basically. And now I want to kind of talk to you guys about the how. So first off, what kind of orbit or distance are you looking to place a small sat in for this project?
Yeah, well, that's precisely one of the tasks I'm working on this summer. And so we're looking at how the different orbits impact the type of data we can collect from the mission. Specifically, just how I mentioned that satellites in low Earth orbit or geostationary orbit have these different aspects that don't allow us to get the type of data we want. So we're studying some different types of orbits that are farther away from geostationary, still within the cislunar region, just to see how that affects us. The one that I am trying to run some simulations on, which is also the one that I'm leaning towards personally, is one of the Lagrange points, but instead of an Earth-Sun Lagrange point, an Earth-Moon Lagrange point. Specifically the L1 Lagrange point between the Moon and the Earth, in which it would be a litigious orbit, because even though those points tend to be more stable, they're not exactly perfectly stable. So instead of orbiting around the Earth or around the Moon itself, it would orbit around a point in space where the attraction of the Earth and the Moon are sort of equal. And that type of orbit allows us to currently, as I'm looking into it, allows us to look at the whole Earth and allows us to study these all different kinds of variabilities. But a key aspect to take into account is that for this type of mission, since it's a small satellite, it won't probably have a dedicated launch vehicle. So we also have to look at different options depending on how we can use different rideshare options to get to these different spots. So even if we do find a perfect orbit that has all the parameters that we need, we still need to take into account how are we going to get there.
And Doug, do you want to add anything to that? Make sure you unmute first.
Yeah, I'm muted again. That was very good. I think the point Jorge made that we really want a position that's far enough from the Earth to see the whole Earth, but also close enough to get to. That's one of the, like you said, that's one of the things we need. A couple of the image from Discover in Jorge's presentation was, that sort of image of the Earth would be, that sort of distance from the Earth would be ideal. But if you noticed in those images, the whole Earth was illuminated, and that's because that satellite is sitting basically between the Earth and the sun at that Lagrange point, and so it always sees the full face of the Earth, the illuminated face. If we're looking at an exoplanet, a planet around a distant star, we almost certainly won't see that face very well, because that would be when the planet's behind the star, seen from our point of view. So we will more likely see the planet in half phase, or like the new moon, or at some different phase. So we really want a location that will see a variety of illuminations of the Earth too. So not only the Earth spinning underneath our satellite, but also the sun essentially moving around. So we see partial day and night, and that variations. What we're trying to understand is how much does the view of the Earth and the things we can measure, how much does it change from day to day with the rotation of the Earth and the continents and the ocean coming in and out of view, and cloud cover changing, and then for over the seasons as the angle to the Earth tilts, and we see more or less of the of the pole of either pole, and then from year to year, maybe there's longer term changes. This year was especially dry, or this year was especially wet, or something. And so by understanding the full range of these things, we can hopefully apply that to the variations we see from extrasolar planets. And so we want a position that allows us to see not just the whole Earth, but also the Earth rotating, which kind of throws out geostationary, which sits above one spot on the Earth. And also we want to see the day-night cycle, which means we don't want to be like where the Discover satellite is at this Earth Lagrange point, even though it's a very cool view.
What kind of factors, elements, molecules, what sorts of things are you looking for to use against, say, exoplanet data?
So right now I think the idea is we're trying to focus on what we can likely detect with upcoming missions in the near future and from exoplanets. And so those are going to be focused in the visible or likely near infrared wavelength band. So visible, the light we can see, the kind of things that are good to maybe indicate there's life on Earth is you can see the absorption from plants. First of all, you can see if there's an atmosphere, the blue sky effect, where the blue light is scattered more than the red, and so you can see if there's an atmosphere. You can see this, it's known as the red edge, which is this absorption where plants strongly absorb light, and you can see as the plant cover increases, this change in brightness between two bands across this edge varies, and so those are all in the visible. Also in that Discover image that Jorge showed, I should have pointed out while it was up there, you could see a glint off the ocean, the sun reflecting back to and we've maybe seen that something similar on extrasolar planets, but we certainly can look for that. And what that tells us is there's something shiny on the surface of the planet. That could be, likely things are ice or water. And by looking at the polarization of that glint, we can get some information about what's causing this reflection. And so that's also in the visible wavelength range. So that's one of the reasons we want to try and have a polarimeter, something that can measure polarization, like your polarized sunglasses. And then finally, in the infrared, that's a great place to look for identifications of various molecules in the atmosphere. Particularly water is the most easy one to see, but also carbon dioxide, carbon monoxide, methane, some of the basic gases that don't necessarily indicate life, but are essentially the easiest ones to detect also, and the most likely that'll be the first ones we detect on an extrasolar planet.
Jorge, what's the next step for you? What are you doing to actually pick an orbit, that kind of thing?
Great question. So currently I'm using some different software packages from both NASA and private commercial entities that allow me to do some different simulations of these orbits that help me decide a few things, which principally, just what view of the Earth the satellite would be getting at any given moment during the orbit. How much would it cost to get there in terms of the fuel and things like that. And we're performing a trait study in which we're putting all these different orbits together, giving them some different important parameters that we're looking for, so that we can sort of give them a score based on how well they fulfill the parameter as much as we need it, so that whichever one comes out with the largest score at the end is sort of the favorable orbit.
Okay. So I have a question from the audience that I'm intrigued by here. Doug, we often use spectral analysis on other planets. Would this mission use spectral analysis on Earth?
Yes. So that's one of the goals. One of the key instruments we hope to have on the spacecraft is a spectrometer that's looking back at the Earth, and that would hopefully have one in visible and one in the near infrared, which are the two sort of most likely instruments we would be seeing other extrasolar planets with too. So yeah, those are key in measuring what kinds of molecules are in the atmosphere of Earth or in other planets.
What future missions, Jorge, you mentioned several future missions, JWST, HabEx, LUVOIR. How would these assist in this particular mission?
These future missions wouldn't assist us. We will be actually assisting them, in the sense that the data that we collect will help the different sort of habitable Earth models, just so that we can, the amount of data we probably get back from these missions will be enormous. So probably using the Earth as the ground truth for this data, we could probably do automated searches for these planets that have similar sort of footprints as the Earth. And hopefully we do get to launch James Webb later this year.
Yeah, soon.
So that one would be the first one, and by this time no changes to sort of the design can be made, but probably from data we collect, and the way we do the measurements of the Earth, we can also dictate sort of instrument parameters for these other future missions that are still in development, and we have time to sort of change the designs a little bit.
Okay, thank you. Jorge, I want to kind of get into how this program has been going for you. What has been the most exciting part of being in this REU this year?
Well, it's been fun after being locked in my house for a year and a half, to sort of get a different scenery, come out here to Mountain View, and meet all the other great REU students that are part of the program. That's been great. The exploring, the different field trips we've been able to take have been amazing. Amazing views that I never thought I would ever see. Working just in this larger project, I found out that John Grunsfeld, he's one of my favorite astronauts, and he's also affiliated with this project. So that was sort of one of the most fun parts about just finding that out. I sort of had like a fanboy moment.
Me too.
I completely understand that. I had the same reaction to being around Jill Tarter the whole time during my REU.
Yes, her too. We had it.
So
We had to watch Contact with her, and that was so
Oh,
so
wow.
amazing.
that's always a fantastic experience. I don't think I'm ever going to forget it. Like, I'm really glad that she continues to do that. So that's great. Doug, what's next? What are we doing next on this?
So this is, I want to give a shout out to Jorge, because this project has been, I and other astronomers have been thinking about this idea for a while. This has been something, but it's always been, especially with me, it's always been level, this would be a great idea, and we could just build the satellite and, have cameras on it, and it would be awesome. But it really needs someone with Jorge's expertise to say, well, this is in practice, this is what you could actually do, and here's, the kind of capabilities you have, and where you can put a satellite, and how big it is, and what size cameras, and how much, how much power do you have on board, and how long can it last? And so it's that the next steps really are the kind of, I think, the detailed engineering work to come up with a credible design that says, okay, here's this, what I think is a great idea, and some other people do too. But that's not enough to sort of sell it to NASA or anyone. We really need to come up with not just here's an idea, but here's a design and a satellite, and here's how it would work. And that's the kind of thing that we're pushing towards. So hopefully, with Jorge's help and the rest of our group, we can come up with a kind of a credible design for a satellite that we can convince people that, yeah, that design you picked really would work and really would answer these questions that you are asking.
That would be really exciting. I would be excited for you and Jorge on that front. That would be great. Jorge, what's next for you when you're done with this REU? You go back to University of Puerto Rico, and what are you majoring in? What are you studying?
Yes, I am currently going to start my fifth and final year of mechanical engineering at the University of Puerto Rico. So hopefully, if everything goes well, I graduate next year. So I'll start looking for different, grad programs. I'm leaning towards, astrobiology and planetary sciences, uh, just to diversify myself a little bit more and not do engineering again. And when I come back to Puerto Rico, I'll just keep working with my regular research projects that I have throughout the year.
Okay, well, good luck to you. Doug, I have one last question from the audience that I think is kind of interesting, sort of a little bit off topic, but not quite. Do we need to broaden our outlook of what it takes to support life? Will life be like what we have here on Earth?
I think I can safely say no, it will not be like what we have here on Earth. No one can disprove me on that yet. So, yeah, and I, we people ask this question a lot, and it's a very good question. Why are you just looking for the Earth? And the part of the problem is, part of the answer is, well, that's the one thing we know to look for. We don't know of any other forms of life, so we, in some sense, don't know how to look for them. And I think we're starting to make advances on that front. And one of the ideas is, we look for things that are in disequilibrium. Like in our atmosphere, you shouldn't have oxygen and methane both at the same time in the atmosphere. What that means is that something is resupplying it, and that something on the Earth is life. There are arguments that it might not need to be life if we saw that. But so if we're looking for things, what people call disequilibrium chemistry is one example of something. If you see something that really shouldn't be there, one possible, not the only, but one possible explanation is life. And I think there's a recent, still very debated example of this with the phosphine discovery, or maybe discovery on Venus. And I think that case is really interesting, and it shows kind of the importance of the kind of work I think we're trying to do here, and that there were some measurements taken from different very large telescopes on the Earth looking at Venus, which is the closest planet to us, and we can see it really clearly with your eyes in the night sky, and we still are arguing a lot about what they mean, or even if they're real. And so when we take these measurements with these really big telescopes looking at planets that are light years away, we're, with this kind of search, we're probably not going to get a sign that says, hey, I'm life, look at me. And so there's going to be a lot of argument and trying to understand what we're seeing. And I think the kind of the main goal of this project is to sort of help define help us understand what we're seeing. And since we know what life like us looks like, that's where we start.
Excellent answer. I want to first off thank you both for joining us today and for an excellent SETI Live. Thank you so much for being here. Thank you again to all of our viewers from around the world. You make this possible. Once again, just a quick reminder, we are a nonprofit 501c3. If you are interested in supporting our programs, please check out our website, seti.org. We'll have a link across the various services. And it doesn't matter if you're watching on Twitter, Twitch, Facebook, or YouTube. We appreciate that you are here. So thank you so much for your viewership and your support. We will be back tomorrow with SETI Live, number 5 this week. This will be another Frontier Development Lab event, and we will have with us a team looking at how solar wind may affect weather on Earth and using machine learning to predict that. So come back tomorrow at 2 p.m. Pacific, and we will be back again. So once again, thank you, Doug, thank you, Jorge, and thank you everyone for watching. Have a wonderful rest of the day.
Cool. Thank you for having us.